So close. So close to the end of the
Yeah,
road.
the sunburn, it's over.
Very nice. Have anything lined up?
Not yet.
It's a market out there. I don't know if it's not a good market. Suppose there's a market. It's a strange time to graduate.
I have one job lined up at the casino. The second.
Yeah, we were talking about this yesterday. That sounds like a really good gig. All right. Last time we started talking about languages and all of the notation that we're going to be using, as well as some additional definitions. So we talked about alphabets, we talked about strings, we talked about the kind of terminology, lowercase letters we're going to be using to represent those strings, as well as the characters that are going to be in languages that we're going to be looking at. As we look at simpler languages, we're most likely going to be looking at, AB, ABC, 0, 1, something that is a very small alphabet, and then languages that you can make with those very small alphabets, because that's usually how, as the alphabet grows, the designs grow in size. And if we want to be able to write things on paper or on the board to learn how to do things with this, it's better to keep things very small. So we talked about that we can concatenate reverse strings, find substrings, look at the length of a string. Lambda was the empty string. Reverse of a string is a superscript capital R. If there's a number there, then we're repeating the string. We then said we have our alphabet, sigma. We can define sigma star, or the star closure, to be any set of strings from 0 or more repetitions of any legal character in the language, I guess in the alphabet. So we could say now that if it's AB, then you could have no characters. You could have only A or B. You could have A, B, A, and literally anything, any string that you could make with any sequence of legal characters of length 0 or more. We defined the positive closure to be the star closure, but we just don't allow for the empty string. So now there must be 1 or more characters instead of 0 or more characters. We talked about that the star and positive closures are always infinite sets. We talked about why that was. We defined a language as some restriction on the star closure of the alphabet. So we're going to replace some additional restrictions, and then we have a set of strings that belong to that language that are in the star closure, and we have a set of strings that do not belong in the language in the star closure. A sentence is just one such string that is in the language. So we can define sentences in the language by just finding strings in the language. We used the example of A to the N, B to the N. So we found the star closure. We found some examples of sentences in the language. We determined that there were an infinite number of sentences in that language. And we found some examples of sentences that are not in the language. So they're not sentences in the language, but they would be sentences in the complement of that language, where the complement is defined to be the star closure minus all of the strings in the language. Questions on anything that we covered yesterday? Went through that very fast. We said that we could define the union, intersection, and difference. We could define the complement of the language as the star closure. The universal set is now just the star closure of the alphabet. We can find and define the reverse of a language to be the set of all string reversals. So any string that is in the language, the reverse of that string is in the reverse of that language. So we can define that as the reverse of the language are all reversed strings such that the forwards string is in the original language. That's how I'm reading that. We can define language concatenation. Now it's all strings where you can break the string into two segments. The first segment is a string in the first language, and the second segment is a string in the second language. So you just concatenate any legal string from the first language with any legal string in the second language, and you get a string that is in the concatenation of those two languages. Mathematically, we get the new language, L1, L2, is every string XY such that X is a string that is a member of L1 and Y is a string that is a member of L2. So again, just getting used to that notation, seeing it in English, seeing it written in a much shorter mathematical language. If you have the language with a superscript integer, we're just going to assume that that is L concatenated with itself n times. So L to the 0 is always defined to just be the set that contains the empty string. L to the first is equivalent to L. L squared would be LL. L cubed would be LLL. So you can think of it as X, Y, Z, where X and Y and Z are all strings that belong to, that are members of that original language. They don't have to be the same string. So we're not talking about string repetition. It's just that you could break it into that many chunks, and each one of those chunks has a string that is legal in that language. Finally, we can define I guess not quite finally, we can define the star closure of a language to be the union of all of these. So we take L to the 0, union L to the first, union L squared, union L cubed, etc. And that is going to be the star closure of the language. Similarly, we have the positive closure of the language, which is just the star closure of the language, but we don't allow the empty string, which is here defined to be L to the 0. So we get L to the first, union L squared, union L cubed. This will get much more interesting very soon, I swear. Lots of definitions, lots of terminology. Any questions about any of these definitions? Anyone want any examples of any of these?
Give me an example of star closure and positive closure.
Yeah. Absolutely. Green today, because I'm feeling green. So if our language is, let's say we allow so our alphabet is just A, B. The language is going to be a single A followed by an arbitrary number of B's followed by a single A. What is an example of a string that is in the star closure of this language?
No form star closure.
So it just means that basically we're going to say that we can concatenate any string from this language an arbitrary number of times. So let's start with just L to the 0. There's only one string that is ever in L to the 0. That is the empty string. So we know, so the examples of the star closure of this language are the empty string. That is a member of the star closure of this language. What is a string that is in L to the first? Sure. What is another string that is in L to the first? ABBA. So this is L to the 0, this is L to the first, this is L to the first. What's an example of a string that's an L squared?
ABA.
Sure. So an example of L squared is ABA. We can break this down into two components. The first component comes from L, and the second component also comes from L, and they're concatenated together. So now you can continue this an arbitrary number of times, where an example of something that's, let's do one more example of something that's in L squared, because these don't have to be the same string. We could have A, B, A, B, 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 A, and that is also, you can break it down into two components. They don't have to be the same length. How about the string A, B, B, A, B, A? Is that in the star closure of the language? Why?
You've got two A's in the middle.
Yeah, so the idea that I want to get here is that this doesn't count. There can't be any overlap between, they have to actually be concatenated. We have to find the end of the first and the second one starts immediately. How about A, B, B, A, B, A? There are two strings in here that work in the language, but there is this extra character in between that we can't fit with the definition at all. So they have to be concatenated. There can't be extra characters in between, and there can't be any overlap. So this is also not in the star closure of this language. Any questions? Right. So we've talked a lot about languages. Now we're going to talk about another way to think about languages and define languages. I've kind of been writing them out as a definition like this, but we can also use a construct to be able to define a language. So a grammar is very similar to the concept of the English grammar. It's a way to determine whether we have a sentence that is well formed, meaning that it's in the language or not. Basically, a grammar says that if a sentence can be derived from the grammar, then it is in the language. If the sentence cannot be derived from the grammar, then it is not in the language. So we'll start with English, because this is something that we are all used to. We're going to define a simpler version of English. And this is exactly the form that a grammar in a programming language takes. We have this idea. Think of it kind of like a variable, because it is not part of the English language. It is a concept. It's a concept that has a word that describes it, but we start with the concept of a sentence. If we can expand this sentence into a sequence of English words, then it would be a legal English sentence. So we're going to say that a sentence is defined to be, that's what the arrow means, a sentence is defined to be a noun phrase, another variable, followed by a predicate, another variable. We now need to further define what each of these variables consist of. So we will define a noun phrase to be an article followed by a noun. We will define a predicate to be a verb. We will define an article to be the word the or the word a. Then a very small version of English. We will define a noun to be either the word boy or the word dog. And we will define a verb to be either the word runs or the word walks. The question I have for you now is, I will give you an entire English sentence. The boy runs. Is this a legal sentence according to this grammar?
Yes.
By the definition, we should be able to start at sentence and eventually, through an expansion of these rules, derive the boy runs. Let's take a look at how that would work. So we're going to start with, I kind of like to draw this like a tree. We have a sentence. We know that there's only one definition here for what a sentence can be. So we are going to break this down now into a noun phrase. And a predicate. A noun phrase, there's only one definition for that. It's an article followed by a noun. So we're going to break that down into an article. And a noun. A predicate is only a verb. Moving on, I'm just kind of doing this in breadth first search order. You can totally do this in depth first search order. It doesn't really matter how you handle this expansion. We'll talk about other ideas of this later. An article is either the or a. Now we have a choice. So we can use our own intelligence to decide when there are multiple possible definitions, what's going to help us to derive this. If we're writing a program, we have to use either some additional intelligence that will help us. We'll talk about that later. Or we have to brute force the whole thing, which is kind of gross. But for now, if we want to create the boy runs, a is not a word in that sentence. The is a word in that sentence. So we're going to select that this article is going to be replaced by the word the. All right. A noun can either be boy or dog. Since boy appears in the sentence, we're going to intelligently replace the noun with boy. And verb can either be runs or walks. So we're going to replace it with runs. And now if we do a depth first search for leaves in this tree structure, we would end up concatenating the boy runs and see that this matches the sentence that we were attempting to derive. Since this grammar can create this sentence would be in the language defined by this grammar. Questions about a kind of a grammar derivation? For now, all you need to be able to do is read a grammar. Throughout this course, you will be writing grammars, which creates a whole different kind of problem. When you want to define a language, can you come up with the rules that isolate that and only that language? Questions on this so far? What is an example of a sentence not in this language? The girl runs. There is no girl in noun or anywhere else in the English language, according to this English language grammar. This is a very small language. There are only 6 words in it. Girl is not one of them. What's another example? Maybe only using the words that are here. Can we use the, a, boy, dog, runs, and walks to create a sentence that is not in the language defined by this grammar?
The boy dog runs.
The boy dog runs. Yeah, there's no way to create a noun. You can't have 2 nouns in a row. It's impossible to derive that. Same with order. We know that articles come before nouns. This is a concatenation. This is not something that can be flipped for any reason. So if we wanted to have something like boy the runs. Already a terrible idea. Boy the runs. That's a great conversation starter. Make sense? So we use logical ors, we use concatenation. We have kind of variable-like concepts here that are not aspects of the language, and we have strings in a language, or strings in the alphabet, I guess.
So if they're getting directly concatenated, then why do we have spaces between them?
There are no spaces here. This is just direct concatenation. Oh, you mean in there? Yeah. Yeah, you're right. We're assuming that wherever we do this, we add a space, I guess.
Oh,
English makes it a little bit more challenging. It's more, the boy runs would be a legal sentence. All right, moving on. We can define a complete grammar to say that grammar can create every possible sentence in a language. So we can further say, I think I've already said this, that if a grammar can generate a string, then it's in the language defined by the grammar. If the grammar can't generate the string, then it is not in the language defined by the grammar. So there are no counterexamples in either way. Grammars always start with the most abstract concept and work their way down to the most concrete concepts. So you can imagine that you have a variable that defines some things that are concrete, and then you have variables that are defined by variables, and variables that are defined by abstract variables, and you slowly work your way up until you have the most abstract variable. In this case, it was sentence. Sentence is the most abstract concept. But we will find that we always start with something like that. We will start with the letter S too. Here's where you start in the grammar that represents the most abstract concept. Starting with that most abstract concept, you want to reduce each of those concepts down into components, components of components, components of components of components, until you have irreducible building blocks of the language. You want each one of these, we call them non-terminals, these variables in the grammar, they want to represent some concept. Grammars are easiest to create if there's meaning behind each one of those non-terminals, just like there's meaning behind any variable that you create in a programming language. This is why you want to use good names for your variables. If you just use letters or useless words, then it becomes gobbledygook, spaghetti code. Nobody can read it or understand it. It's the same with grammars. You want your non-terminals to have meaning. And I would even argue that you want to name your non-terminals based on, similarly to how you name your variables. What do they represent? What components of the blocks of this language does it represent? So of course, grammars exist for programming languages because programming languages are languages. Anyone want to take a guess at the complexity of a grammar for the Java language?
not as complex as English.
Yeah, English has some pretty ridiculous grammar rules. I'm not sure you could build a reasonable grammar. There'd just be it's what I'm looking for. Counterexample after counterexample. So we're actually going to go look at a Java grammar. So if you've taken any kind of programming language class before, you will have learned about identifiers, Obviously, people in here have seen that before. We now break this down into qualified identifiers, qualified identifier lists, compilation units, import declarations, type declarations. And we can now further define and create. Here are all of the possible words that a modifier can represent. Anything that starts with a capital letter is a variable. Anything that is a lowercase letter is a keyword. And you can see that there is a lot to this grammar. It's not shown in exactly the same way, but we have different groups for different kinds of symbols that could have certain meaning. So assignment operators. These are all of the assignment operators that are legal in Java. Infix operations, prefix operations. And this tells us kind of the building blocks of a legal Java instruction. What kinds of instructions can follow certain kinds of instructions? What needs to be done? So this is it.
Honestly, kind of shorter than I wanted to be.
Yeah. Good grammars are often shorter than you would expect them to be. The logic that you can create with this grammar is much more complicated than the grammar itself, which is why we study them. If you're going to write your own language and write a compiler for your own language, all you have to do is find the rules that convert the language as it is written into some logic. We could map, based on this grammar, all of these rules into associated assembly instructions. I guess JVM instructions, but you could do that. That is what a compiler does, is it is the translation from this concept down into assembly instructions. So I'll give you the official definition of a grammar. I don't like to start here usually. Sometimes I will. But if you read a textbook, it will look something like this. And now that you have a little bit of experience with them, I'm hoping that this definition makes more sense. So a grammar G is defined as a quadruple, which is just a tuple with 4 elements. So the grammar, if you're going to tell someone or show someone formally, here's a grammar. You need to include 4 pieces of information. You need to include a finite set of objects called variables. We call these non-terminals as well. These are the variables. In the past example, it was the sentence, noun, article, verb, noun phrase. T are the terminal symbols. These are the pieces of the language, the actual elements of the alphabet. So we had English words as the terminals in the grammar that we looked at. So you would have a set of variables, a set of terminals. We have S. We have the start variable. This is where you start whenever you want to create a legal sentence from this grammar. So in the prior example, that was the sentence. Every sentence starts with a derivation, starting with the concept of sentence and expands from there. It's the root of the tree that I drew. Finally, we have P, a set of productions, and those are the actual rules, every line of the tree. So going back to too much. We have the start non-terminal. We have the set of non-terminals. We have the set of terminals. And then we have the set of productions. Each one of these that tells us the rules of how the expansion is done. If you list those four things, then you have fully defined the grammar. That's everything that a computer would need to be able to do, to know in order to use that grammar for some reason. If you're showing it to another human, just the productions is enough. You can assume for like the top left element is the start. All right, so we have a definition for a grammar. Let's get another one. Questions I'll be asking you about this grammar. What is the language defined by the grammar? And also, if we remember back to discrete, what proof method could we use to prove that the grammar is correct? Here's a grammar. And again, we're going to use that definition of a grammar from before where we have those four elements. So we have the non-terminal S. We have the terminals A and B. So those are members of the alphabet. We know that the start non-terminal is just S, and the set of productions, we have two rules. We can define S either as the terminal A followed by the non-terminal S followed by the terminal B, or we can define S to be the empty string. So now, thinking about what language is defined by this grammar, interesting. You can see one possible expansion here from this grammar. We start with S. And note that when we're writing the rules, we just use a single bar when we're actually showing the examples of this is an actual derivation. We use the kind of double horizontal bar. So we are going to apply this rule to this non-terminal, expanding this to be that, which is what you see there. We still have a non-terminal. We're going to keep the terminals here, and we're going to expand this S now with this rule. So leaving this A here and this B here, which is this leftmost A and this rightmost B, you see that this S is replaced to be the ASB that is in the middle here. We are then going to apply the second rule to this S, taking the capital S and turning it into the empty string. So you end up with the string AABB. If you want to shorthand this, you can use the forget exactly what this is called, but it's kind of like a general implication from discrete. But via the star closure of this, you can derive from S that you can get this sentence. So this sentence is in the language defined by this grammar. So now the challenge that I have is, can you define the language that this grammar represents? Could you write that in some form of notation? Or failing that, could you write some English description of that language? Think about it for a bit. See if you can come up with it.
So English description goes, but you could say it's a language that includes any number of A's followed by the same number of B's, including the empty string.
Yeah. So this defines the language. A to the N, B to the N. That same language that we saw yesterday. N A's followed by N B's, where N is some constant. That N can be 0 if the first S immediately becomes the empty string. We know the empty string is in the language. This N just happens to be the number of applications of this rule, because this rule, there's no way to generate more S's on the right-hand side than there are on the left-hand side. So the number of applications of this rule is that N, and this is kind of your terminator. You can choose it to be an A100, an A101, A102. Reference fell flat. Different types of Terminators from the Terminator movies. All right, so if we have, A cubed, B cubed, we'd have A, B, B, B. We apply this rule, this rule, this rule, this rule. This rule n times followed by this. Given that information, if I were to ask you to prove that this grammar generates this language, I'm not going to ask you to do it, but what would the appropriate proof type be? If we remember that our different proof types from discrete. It's been a while. And or who knows if it was actually gone over.
I don't remember going over any proof types of induction.
That's the right one.
Oh, there we go.
This would be an inductive proof because you want to be able to say, if we can generate a to the n, b to the n, then can we generate a to the n plus 1, b to the n plus 1? And how would you do it? So if you could generate we want to say a to the k, b to the k, which we know we can do by saying we can go k repetitions of this followed by this. How would you generate the string a to the k plus 1, b to the k plus 1? You would say one more iteration of this would show that. And then you just need to tie it to reality somehow by showing that this grammar can generate a to the 1, b to the 1, or a to the 0, b to the 0. And then you have an inductive rule that allows you to generate k plus 1 for whatever k you generated. And assuming that's k, then k plus 1 for that. And assuming that, k plus 1 for that. And it creates kind of a domino proof where you get two rules. You say, one, this grammar can generate a to the 0, b to the 0. And then two, you can show these two things, then you have shown that this grammar can generate this. It doesn't say that it's all that it can generate. But there are no other, the next part of this would be to say, there's no other possible way to generate a sequence of these productions. So this would mostly get you there. Again, I'm not going to have you doing proofs of most of the proof types from discrete. There is one very important proof type that actually has nothing to do with proofs in discrete that we will be focusing on in here. But we'll spend a lot of time on that when we get to it. And it's challenging and deserves a lot of time and attention. Does that make sense? Does this tie us back? We've seen induction before. Do these two rules make sense as to kind of how this is a sequence of dominoes? You set up the first domino. We can tie this to reality. This grammar can generate a to the 0, b to the 0. How would we prove that? I would say there exists a sequence of applications of these productions that generate this exact string. What is that sequence of productions? Just the second one. You just do that immediately, and you generated a to the 0, b to the 0. And then to show 2, we would say, okay, we know that to generate a to the k, b to the k, we do n applications of this followed by that. It actually doesn't matter. We just take for granted that we can make a to the k, b to the k. How do we go from a to the k, b to the k to a to the k plus 1, b to the k plus 1? Somewhere in that derivation, you just do this one more time. That'll get you there. Questions on the proof type? Questions on how you would do that? Again, I'm not going to ask you to do it or really anything like it in the class, but I think that it ties well back to discrete and kind of shows you why and how we care about these proof types. Okay. Now it's your turn to write some grammars. We're gonna come up with a language that's very similar to the language that we just saw. Can you write the rules for a grammar, starting with a start non-terminal that generates a to the n, b to the n plus 1? So your first rule is gonna start out looking like s arrow something, because we have a start non-terminal. But just find the sequence of productions that's able to generate this language. If you're stuck getting started, think about how is this similar to and how is it different from the last grammar that we looked at. You can use that as a reference because this grammar is not too far removed from it.
Sorry, looking for the definition or the derivation.
The sequence of productions. So you're going to write the production rules for the grammar such that the only strings that it can generate are the strings defined by this language.
Really just be the same thing with the B.
How so? I think you're on the right track.
Like, would it be like, you have the same for the empty string, and then above that you would have the A and the S and B.
It's an intriguing idea. And I would argue that there are some counterexamples. Like for instance, if the very first rule you apply is S arrow lambda, that says that the empty string is in this language. Is the empty string in this language?
Actually, no.
It is not. Give people just another minute or two. Is it a question or do you have an answer?
Yes.
Let's wait just a minute or two for people. In the meantime, go through and see if you can verify that this works for all of those and there are no such counterexamples. You have an answer? Thinks they have an answer? I think that's most of us. It's totally okay if you don't. What logic did we go through to find an answer? How did you think about the problem? And how did you work your way toward a solution? And you want to describe their thought process? Yeah.
I tried to find how the first ones were generated, how it relates to the actual rules, see if I could find a pattern that I could use to apply that.
Yeah. Yeah, okay, I like that. I like to think of this as, all right, we're gonna have some string that looks like this, where we have n of something, 1 of something. And we know that these are A's, these are B's, and this is a B. Right? Do we agree that this layout is what that language is calling for? So this could be 0, 0, 1. This could be 2, 2, 1. This could be 3, 3, 1. So what we have is exactly what we had before. This is A to the n, B to the n, but there's an extra B at the end. So this is the same kind of looping construct or looping mechanism that we did before. So we're actually gonna write exactly the same rule, and I'm gonna write this down below that so that I don't run out of room. So we're gonna say S arrow A S B, because that produces exactly this. Now to terminate the grammar, instead of having the empty that we did before, we need to be able to produce the extra B. So we could say something like S arrow B. This doesn't quite create this, but it creates something very similar. Yeah,
Well, what about N is 0 and it's just B?
yeah, there's no way to generate. If you don't do this at all, you create B, which creates A to the 0, B to the 1. This is more like if this B instead appeared here, rather than kind of at the end, because we're expanding in the middle here. So we're kind of, every time we create an A and a B, we create the outermost A and B, then the next A and B, and the last thing that we do is right in the middle. So it more so creates this. But I'm able to get to that answer by thinking about the breakdown of this language of saying there's an extra B at the end, when really the grammar that we've written says there's an extra B in the middle. Does that make sense? How are we doing? I like to do this in all of the classes that I do. It makes it so that not everybody has to contribute or be able to really vocalize what's going on, but just give me thumbs that tells you kind of a level of understanding of this makes perfect sense. I mostly get it. There are a couple things that might be slightly unclear that I could use a couple of more examples for. I get the basic idea, but I need a little bit more experience with this to really feel like I understand what's going on. I don't know what's going on, please help me. So something like that, and you can hide it if you want, just some way to communicate with me how this feels to you. So, yeah, let me know. And it's perfectly okay anywhere on that. This has nothing about you at all. Yeah.
It reminds me of one of algorithms, how I think I had Boji on the
Yeah.
trying to like teach you to think recursively.
Yeah. Yeah. This is, you will be thinking very recursively when you're creating grammars. Yes. Okay, we definitely have more, we have more of these to come. There will be a lot of practice with these. So I think we'll move on to the next one for now, and we'll come back on an as needed basis. So the solution to this. Here's another such solution. You can also use ORs. So you can do this to avoid using multiple of these. So these are two additional solutions from the one that I gave. So a grammar is not a unique solution. There are multiple solutions to grammars, just like this. So it's not quite a math class, but maybe there are multiple equivalent expressions that represent the final answer. So if you do not get exactly what I get, that does not mean that it's wrong. You may want to logically connect your answer to my answer to make sure that, are these logically equivalent? The answer may very well be yes. So this or here says that we don't want to write two productions. We can just turn this into a single production with multiple outcomes. So two grammars are equivalent if they generate the same language. We are unfortunately out of time already. I thought we were going to get just a little bit further. No issues with that, because I said yesterday we'd get to start talking about the first kind of automata. We'll talk about that on Monday. if anyone is curious or wants to provide any feedback about how this first week has gone, especially with how small this class is, hang out around class, let me know how things are going for you and how I can help you to start the class off on the right foot. Anything that I can do to make these lectures clearer, better, easier, let me know. Have a great weekend and I will see you on Monday.